Okay, our final class of functions that will differentiate. 3.9, inverse trig functions. And this will be a little bit redundant in places with some things we did in the review chapter. In section 1.6, we introduced inverse functions and logs and stated the definitions there of the inverse trig functions. So we'll go through now and differentiate inverse trig functions, and we'll do it not really using Theorem 3.3, but using the technique we had in proving Theorem 3.3, where we differentiated the inverse of a function in terms of the derivative of a function. And this is our final class of functions that we'll encounter in Calculus 1, and likely the final class of functions you'll encounter in Calculus. I've mentioned maybe in passing, hey, we get done with this, you know as much about differentiation as anybody. You know how to differentiate algebraic functions, you know how to differentiate trig functions, inverse trig functions after this, logs and exponentials, you're good to go. In some sense, that's all the functions you're likely to encounter as an undergraduate. There's some other functions out there. They're a touch more esoteric. And there's actually a whole branch of math called special functions. What makes those functions special is probably some applied problem. They represent solutions to particular applied problems. But you're unlikely to encounter those in your undergraduate years at least. Okay, so you're good to go with differentiation after this section. Let's recall from section 1.6, we had the following. We'll have graphs of these functions here shortly. 1.6 goes through a rather detailed explanation as to why these are the definitions of the inverse trig functions. But cosine inverse, oh, quick warning, not to be confused with reciprocal. That little -1, as usual, means inverse function. It doesn't mean reciprocal. Sometimes the little word arc, A-R-C, is called arc cosine and arc sine. The textbook is big on using the arc notation so as not to confuse these with 1/overs with reciprocals, because they're not, they're inverse functions. You need to get used to this inverse function notation because it's everywhere. So we'll define y as the cosine inverse of x, if and only if the cosine of y equals x, and y is an angle from a particular interval. For the cosine inverse function, we get out y values between 0 and pi. You're actually being given the range of these inverse trig functions in each of these. Y equals sine inverse of x, if and only if the sine of y equals x and the angle, the y value, is between -pi_halves and pi_halves. Tangent inverse, tangent y equals x, and y is between -pi_halves and pi_halves, excluding the endpoint. Tangent of pi_halves and tangent of -pi_halves, neither are defined. So that puts some constraints on what we can get out of a tangent inverse function. And so forth. Secant inverse, cosecant inverse, cotangent inverse. Let's look at the last one. Y equals cotangent inverse if and only if the cotangent of y equals x and y is between 0 and pi. Okay, so we're smooth sailing on 1, 2, 3, and 6. Secant inverse and cosecant inverse. Shockingly, there's not even a universal agreement on how to define these sometimes, especially the secant inverse. We'll make a comment shortly about that. Here's the definitions that we're going to use. For our definitions, we'll take the range of the secant inverse to be between 0 and pi, excluding pi_halves. Not everybody does that. And for cosecant inverse, we'll take the range to be -pi_halves to pi_halves, excluding 0. That one's a little more standard. But with these definitions, we get the following relationships. And we'll really just justify these by looking at graphs more than anything. Secant inverse is pi minus cosecant inverse, or pi halves minus sine inverse of 1 over x, or cosine inverse of 1 over x. It's the outer ones I want to relate. Secant inverse of x is the same as cosine inverse of 1 over x. See, how did, forget the inverse stuff, how did secant and cosine relate? Wasn't it secant's 1 over cosine? Okay, well, the 1 over comes in a different place, but we've still got some sort of 1 over relationship related to secants and cosines. In this case, secant inverse and cosine inverse. What was cosecant? 1 over sine. Cotangent was 1 over tangent. We get a similar type relationship for cosecant inverse, the punchline being cosecant inverse is sine inverse of 1 over x. Cosecant inverse of x is sine inverse of 1 over x. The relationship between cotangent and tangent inverse is a little more subtle. Cotangent inverse of x is pi halves minus tangent inverse. Some identities that result from these definitions of the inverse trig functions. And let's not worry about details on that. I'm happy to take those as given. We're here to do the differentiation. The textbook does caution that the choice of secant inverse of x for x negative is not universal. Sometimes the choice of pi halves to pi for x negative is what we get out as that part of the range of the secant inverse. As we did, by having that, then this relationship holds. Other sources take secant inverse of x for x negative to be between negative pi and negative pi halves, yet others choose pi to 3 pi halves for x negative. There's a picture in the book. I don't really want to sweat over that. It affects what the graph looks like. So what I really want to concentrate on probably really is just the first 3. Though tangent, cotangent, arc cotangent, cotangent inverse, I kind of like that one. It's clean. The other 2, maybe there's some ambiguity. The other 2 are not continuous. So if we look at a graph of, make it bigger for the first 3, these 3 I like, smiley face. Here's what the graph of the sine inverse function or the arc sine function looks like. I warned you the book likes to use the arc notation. Same thing as sine inverse. So we put in a value between -1 and 1, and we get out an angle between negative pi halves and pi halves. Notice what we've done is taken a sine function, interchange the roles of x and y. So instead of having a sine function that oscillates along the x-axis, we get a sine function that oscillates along the y-axis. But then I can't have a function if it violates the vertical line test. So we've taken a sine function that oscillates with its axis along the y-axis and erased everything except for this part here. This covers all values between -1 and 1, and it covers them exactly once. So I haven't violated the vertical line test. If I extend this sine wave a little bit more, it's going to start arching back towards the y-axis and will violate the vertical line test. So that's how we restrict the domains on sines, cosines, tangents, and the rest. See section 1.6 for more details. But this is what we get for a graph of sine inverse. Cosine inverse looks like this. It's half of a wave. Both of these are halves of waves of sine and cosine. The convention is, in all of this, we want these inverse, all 6 inverse trig functions to include the acute angles. We want to get out of them the angles between 0 and pi halves. And for these 3, in addition to that, we want to make the inverse trig functions continuous. And that's what produces these. So we certainly want to include the acute angles, angles between 0 and pi halves, angles between 0 degrees and 90 degrees. Acute angles are angles that can appear in triangles. So it's useful to have those as part of the definitions of each of the inverse trig functions. For arctangent, remember what the wave of a tangent function looks like. This is a single wave of a tangent function. It's a full wave. It's 1-to-1. That's been revolved around the line y equals x. So take a single wave of the tangent function, centered at 0, passes through the origin. and interchange x and y. That produces a graph of the arctangent function. Again, it includes the angles between 0 and pi halves, and it's continuous. These could have been done different ways. This is the standard way that they're chosen to be done. Let's look at arctangent, or arccotangent, or cotangent inverse down here. Same story. The wave has a slightly different shape from what we had from tangent. And arguably the shapes are the same. They're kind of mirror images of each other, it seems. But this also includes the angles between 0 and pi halves, excluding 0 for some technical reasons. And it's continuous. Now, about the other two, arcsecant and arccosecant, these include, both of them, the angles between 0 and pi halves, except for 0 for some technical reasons. And neither are continuous. Neither could be continuous if you'll think back to what the graph of a secant function and the cosecant function looks like. Were we to continue this without having restricted the domain, we'd end up with a big C-shaped curve. And of course, that'd violate the vertical line test. Over here, we'd end up with a C-shaped curve backwards, violating the vertical line test if we continued. What was commented about other books' choices for the range of the arcsecant would be, we include this piece and we include a piece over here. Maybe not this piece, maybe something down lower, or maybe something up higher. Maybe we can include the part that starts here and goes to 3 pi halves. I think that was mentioned somewhere in there. But in all 6 cases, what's included is sort of the entire behavior of that function. What can you put into, say, a cotangent function, a cotangent inverse function? Anything. We've included a single wave. We've included all of the possible behavior for a cotangent function, or a tangent function, or a sine and a cosine. And we've included all the possible behaviors here. Just these are a little messier because these are of necessity not continuous functions. So there's the definitions. Hands-on, we'll really not much concern ourselves with the cosecants and cotangents. Maybe not even cosine. It's the functions themselves we might concentrate more on. In terms of the differentiation, sine, tangent, secant, or arcsine, arctangent, arcsecant, those will be interested in the derivatives, and the cofunctions, the arc cofunctions, are closely related to those. In terms of actually evaluating arcsines and arccosines and that kind of thing, we'd likely use the top 3 for actually evaluating angles. You pick up a calculator, you paid, I don't know, $10 or $15 for a scientific calculator. It'll have inverse sine, inverse cosine, inverse tangent, and it probably won't have these other things built into it. And you could program it easily for a few keystrokes to deal with these others. But depending on the question, as the functions we'll deal with, if I'm really computing arcsines and stuff like that, I'll probably use these top 3. This is a calculus class. That's not really our focus. Our focus is on derivatives. And we'll probably most likely deal with the arcsine, arctangent, arcsecant. The arc cofunctions, we'll mention those in passing, but it's the arc functions themselves, not the arc cofunctions, that'll play the dominant role, as will become apparent when we go through and figure out how to differentiate these things. First, let's look at just a little example to illustrate this. This is really something we could have done in section 1.6. I'm going to streamline it for the most part. They ask us to use reference angles in an appropriate quadrant to find the angles, sine inverse of a half, sine inverse of -1 over the square root of 2, and for notational variety, the arcsine, the square root of 3 over 2. All right, part A and part C, you know those involve special angles. Those will be easy. Part B is slightly more interesting. For more details on this kind of thing, see section 1.6. Okay. with a knowledge of section 1.6 and a knowledge of special angles. I'm going to whip through part A and part C pretty quick. Well, if theta is the sine inverse of a half, let's represent it with theta because it's an angle, then we need the sine of theta to equal a half, and we need theta to be in the range of the arc sine function, the sine inverse function. That is, we need theta to be between negative pi halves and pi halves. Well, between 0 and pi halves, sine is positive. Between negative pi halves and 0, sine is negative. So we're looking for an acute angle, one between 0 and pi halves, because the sine is positive. Here it is, sine is positive. And do you know an acute angle whose sine is a half? Yeah, that's pi 6. So I'm appealing to your knowledge of special angles in dealing with this. These would be not particularly good test questions in terms of this section. This is sort of review of properties of inverse trig functions. All right, this one's a little more interesting. Also not a good test question for this material. There's no calculus to it. Suppose we're looking for sine inverse of negative 1 over the square root of 2. Well, let theta be the sine inverse of negative 1 over the square root of 2, since it's an angle denoted by theta. Then we need the sine of theta to be negative 1 over the square root of 2, or if you like, negative square root of 2 over 2. Maybe this number rings a louder bell than this one does. I mean, they're equal, whatever. If you don't mind irrational denominators, don't care which one you use, but whatever sounds most familiar to you. And again, we need the angle to be in the range of the inverse sine function between negative pi halves and pi halves. Okay, this time the sine's negative. Well, that's not an acute angle. That's not an angle in the first quadrant because its sine is negative. It must be an angle between negative pi halves and 0. Between negative pi halves and 0, it must be a quadrant 4 angle. So here's where the reference angle stuff comes in. Do you know an angle that has a sine of, the absolute value of this, has a sine of square root of 2 over 2? Yeah, sine of pi force is square root of 2 over 2. Sine of pi force is square root of 2 over 2. Okay, so the reference angle must be pi force, the reference angle. The angle between the terminal side of the given angle and the nearest part of the x-axis. So this is the reference angle and it's pi force. So we're dealing with a reference angle of pi force and an angle in quadrant 4 and an angle between negative pi halves and 0. That angle itself must be negative pi force. So the angle's negative pi force. You knew it had to be between negative pi halves and pi halves because the angle theta comes out of an inverse sine function. And by definition, that's the kind of angles that come out of an inverse sine function. Now, I know there's other angles out there that have a sine of negative square root of 2 over 2. But there ain't but one of them in this interval here. That's the restriction of the domain of the sine function that leads to the definition of sine inverse function as actually as a function. There's only one angle in this interval that has a sine of negative square root of 2 over 2. Yeah. There's an infinite number of other angles with that sine, but only one of them's in here. And finally, in part C of this one, they want us to find the arc sine of square root of 3 over 2. So we want the sine of theta to be square root of 3 over 2, and we want theta to be in that same interval. This time, positive, acute angle, special angle, it's pi thirds. So let me depend on some knowledge from section 1.6 or pre-calculus or high school about special angles. And there you go in terms of evaluating inverse trig functions. Let's do another one. Let's also do number 14 while we're here. Ooh, a limit question. Find the limit as x approaches negative 1 from the positive direction of the cosine inverse function. Okay. I'm pretty much lacking in limit knowledge of these functions, but I know how to graph them. So we were given the graphs, so I tell you what, let's analyze this by looking at the graph, and let's go back to Dr. Bob's anthropomorphic ideas about limits, about trying to pass through a point or trying to contain a point. First, notice negative 1 is a left endpoint of the domain of cosine inverse. Here's cosine inverse or arc cosine. Here's -1, the x value. Yeah, the domain of the arc cosine function is the interval -1 to 1, including the endpoints. The domain is -1 to 1, including the endpoints. So we want to see what happens when x approaches -1 from the positive side. So that would be x values along here. It'd be points on the curve along here. As x approaches -1, those points in this curve trying to contain this point. Let me say contain instead of passes through because it's a one-sided limit. Passes through seems to indicate both sides. And we're looking at a one-sided limit. So the curve tries to contain this point. Does it or doesn't it? Well, it's been a while since we've played this game. It's a limit question, so it doesn't matter. By the way, it does, but that doesn't affect the limit question back from early on in chapter 2. But the function tries to contain this point. This is the point -1 pi. So the limit as x approaches -1 from the positive side must be pi because the graph tries to contain the point -1 pi. So that one-sided limit must be pi. So easy enough if you've got the graphs and you think about trying to pass through or trying to contain in the case of one-sided limits points. Let's go to, where am I going here? Back to the notes. And let's deal with some differentiation. So what's to follow is we're going to differentiate sine inverse. Give an example. Differentiate tangent inverse. Give an example. Differentiate secant inverse. And I guess I don't have a specific example of that one. But notice what we're differentiating is sine inverse, tangent inverse, and secant inverse. So we're not doing the inverse cofunctions yet. So as promised, first we'll go through these three. All right. Claim is, if we differentiate sine inverse of u, we get 1 over square root of 1 minus u squared du dx, provided the absolute value of u is less than 1. Yeah, sine inverse function has a domain, -1 to 1. So we'd have to have the stuff that goes in between -1 and 1. They've eliminated -1 and 1 as input. Oh, that's because of this square root 1 minus u squared in the denominator. So we lose 1 or -1. We'd get division by 0, and we can't divide by 0. All right, so what we're going to do is establish these just when u is x itself, and then the more general result, little arrow, will follow by the chain rule. Okay. Well, how do we prove theorem 3.3? We looked at the inverse function in a certain light. So here we've got y equals sine inverse of x. Well, that means sine y equals x and some other stuff. It means the angle we get out at the y value comes out of a sine inverse function. What was the range of sine inverse? It was -pi halves to pi halves. So that's in the background of this story as well. So we require sine y equals x and some other appropriate stuff. The other stuff in this case is y is between -pi halves and pi halves. But let's take this equation and say, hey, the sine inverse function is implicit to this equation. So let's differentiate implicitly, requiring the chain rule. So we'll differentiate with respect to x, sine y, left-hand side, and differentiate with respect to x itself, the right-hand side. What's the derivative with respect to x of sine y? Well, that's a composition of functions. The outer function is a sine function. The inner function is y. Do you know what y is explicitly? Yeah, you do this time. Yet we're still differentiating implicitly. So differentiate the sine function, gives us a cosine function. Rewrite the inner function, as a chain rule tells you to do, and then multiply by the derivative of the inner function. Then multiply by the dy dx. Right-hand side, you're just differentiating x. We just get a 1. And solve. So we got an equation involving dy dx. It has happened so many times with implicit differentiation. Solve for dy dx, and we get 1 divided by cosine y. All right. But we can do better than that. They gave us a function, really, they gave us a function of x, so give them a derivative in terms of x's. It's got this cosine y in it. We know the sine of y equals x. Does that allow you to tell what the cosine of y is? Two answers, sort of and yes. Sort of, unless I've got more information, and we do have more information. We've got y coming out of a sine inverse function. Y must be between negative pi halves and pi halves. Hey, cosine of y. What is the cosine of y for these angles? If you'll think about the graph of a cosine function, cosine of an angle is greater than or equal to 0 when that angle is between negative pi halves and pi halves. Think about the graph of a cosine function. Pause the video and go look up a graph of a cosine function. Yeah, the cosine will be greater than 0. Also, if we take the Pythagorean theorem, cosine squared plus sine squared equals 1, and solve it for cosine y, we'll get cosine y equals plus or minus the square root of 1 minus sine squared, but we know it's not the negative for these values of the angle because the cosine function is greater than or equal to 0. So we can choose the positive square root of, so I'll put the plus sign here to emphasize that. We get cosine y equals positive square root of 1 minus sine squared square root of, because we know cosine y is greater than 0, because the angle y is between negative pi halves and pi halves, where the cosine function is non-negative. Take the positive square root. So we've got cosine y is 1 minus sine squared square root of. And we know sine y equals x from right there. So replace sine y with x to get cosine y equals 1 minus x squared square root of, positive square root of. So can you write dy dx equals 1 over cosine y in terms of x's? Yeah, replace the cosine y with this stuff here. And you get dy dx, the derivative of the sine inverse of x with respect to x, is 1 over 1 minus x squared square root of. You know, that's what we were claiming. Then with the rest of it following by applying the chain rule. We'll state all three of these derivatives we're about to deal with generally where it's been combined with the chain rule, and we'll prove the special case and then say the general case follows by the chain rule. So if u of x is simply x, then we've done it. This is 1 over here. Otherwise, you need the chain rule to finish up the little additional du dx on the right-hand side. We did so much of this in the previous section with the chain rule and inverse functions. So derivative of sine inverse of x is 1 over 1 minus x squared square root of. Let's illustrate an example. Find the derivative with respect to t of y equals sine inverse of 1 minus t. Okay, in symbols of the theorem we just had, we've got the u of t function being 1 minus t. So du dt is just negative 1, 0 plus negative 1. And when we differentiate the sine inverse of 1 minus t, it's a composition of functions, differentiate the sine inverse. Okay, it's kind of wild. All the trig stuff disappeared and you get algebraic stuff, and that's what happened. We get 1 over 1 minus that stuff inside the sine function squared. 1 over 1 minus u squared, it was stated in terms of the theorem, and u is 1 minus t. So we get 1 over 1 minus the stuff inside the inverse sine function squared, 1 over 1 minus t squared, and then you'll multiply by the derivative of the stuff inside. The derivative of 1 minus t is negative 1 with respect to t. And if you like, we can clean that up a little bit. As usual, I'm happy with this as the derivative, unless I'm going to do something to it. Was a composition of functions. Apparently, we had to use the chain rule. Yeah, it was the sine inverse function composed with the 1 minus t function. Let's do another one. Let's differentiate tangent inverse. Claim is derivative of tangent inverse of u with respect to x is 1 over 1 plus u squared du dx. In particular, the derivative with respect to x of tangent inverse of x is 1 over 1 plus x squared times 1. So let's show that for the x. We know that if y equals tangent inverse of x, then tangent y equals x, and you know some stuff about where the angle y is. It was between, for tangent inverse, between negative pi halves and pi halves, excluding the endpoints, by the way. Okay, but we've got then an equation that relates x and y that we can differentiate. Can you differentiate this equation? Can you differentiate tangent inverse of x? Well, that's what we're trying to figure out. So we've translated that question into a different question. We do know how to differentiate both sides of this. Take a derivative of tangent y with respect to x. Take a derivative of the right-hand side x with respect to x. Right-hand side has derivative of 1. Left-hand side, this is a composition of functions, the tangent function with a y function inside it. What's the derivative of tangent? Secant squared. So differentiate the tangent function, the outer function, to get secant squared times y, multiply by the derivative of the stuff inside. Derivative of y with respect to x. Puts a dy dx over here. Dy dx is what we're looking for. Solve for dy dx, divide both sides by secant squared. We get dy dx is 1 over secant squared y, and this one is similar to the last one, only easier. Hey, doesn't secant squared equal 1 plus tangent squared? One of those identities related to the Pythagorean theorem. See chapter 1 for some review material on that. But you should know cosine squared plus sine squared equals 1. That's the Pythagorean theorem written in trig functions. From that follows 1 plus tangent squared equals secant squared, and that's the one we're using here. 1 plus tangent squared equals secant squared. And it's also true that 1 plus cotangent squared equals cosecant squared if we were dealing with cofunctions. But we get secant squared is 1 plus tangent squared. You know what the tangent of y is? Yeah, it equals x. So we get 1 over 1 plus x squared, and that's all we needed. The derivative of tangent inverse of x is 1 over 1 plus x squared. It's this thing here. Combine it with a chain rule to get the general statement. All right, so that one was cool. That worked out a little more cleanly than the previous one. In the previous one, we had a square root, when we had to explain away the square root, why we took the positive square root, not the negative square root, or not sometimes positive square root, sometimes negative square root. This is the easiest one of the 3 we'll do. Let's illustrate it with an example. Find dy dx when y equals tangent inverse of the natural log of x. Okay, we got a composition of functions here. We got an inverse tangent function with a natural log function inside it. In the notation of the theorem we just stated, we'll have u of x as that inner function. It's the natural log of x. So by the way, the derivative of the derivative of u with respect to x, the derivative of the natural log function is the 1 over function. So du dx is 1 over x. That chain rule will stick that on the end. I'm not really that gung-ho about keeping up with the u's and that kind of stuff. I've got my square brackets and my little arrows, and it really does all the heavy lifting of that kind of thing for you. So if you want to differentiate this composition, we'll differentiate the outer function. What do you get when you differentiate a tangent inverse function? 1 over 1 plus the stuff inside squared. So we get 1 over 1 plus the stuff inside squared. Here I almost got a little picture of the derivative of tangent inverse. The stuff inside is natural log function. Okay, chain rule says we'll have to multiply by the derivative of that stuff inside, that natural log function, and that's 1 over x. We can rewrite it if you're so possessed. So easy enough with all the rules we know in terms of derivatives. All we've done is extended it a little bit by adding our knowledge of how to differentiate sine inverse and tangent inverse. Let's do secant inverse. Okay, tangent inverse, I stand by this. That was the easiest of the 3. This one's got an absolute value in it. We'll have to explain where that comes from. All right, so we'll differentiate secant inverse, and rumor has it we get the following. Derivative with respect to x of secant inverse of u is 1 over the absolute value of u times the square root of u squared minus 1 du dx stuck on the side by the chain rule. valid for absolute value of u greater than 1. Yeah, the only thing you can put in a secant inverse function is numbers greater than 1 or less than -1. That is, numbers that satisfy this. Except you could use 1 and -1. What's wrong with those? Oh, we'd have division by 0 if you were 1 or -1. The existence of the function isn't the problem at 1 and -1. It's the existence of the derivative that's the problem. All right. Guess what we're going to do? We're going to say y equals secant inverse of x means secant y equals x and some other stuff. So take the statement of the function we're interested in, secant inverse of y, secant inverse of x, write it as y. Rewrite that as a new equation, secant y equals x. The original equation is implicit to this, and there's some other details. You only get certain angles out of the secant inverse. More of that shortly. Differentiate this implicitly with respect to x. Derivative with respect to x of secant y equals derivative with respect to x of x. Right-hand side's 1. What's the derivative of secant? Secant tangent. Derivative of secant of y with respect to x would be secant y, tangent y, chain rule, times dy dx. We're differentiating with respect to x, requires a chain rule. This is a composition of functions. The outer function is secant, so it gets differentiated away to become this secant tangent. Inner function is y, so it gets plopped into those two, and then the derivative of y with respect to x added on by the chain rule. Okay. So, well, I can go one more step without any problems. dy dx then is 1 over secant y tangent y. Just solve this little equation for dy dx. Thing is, I want to get rid of the secant y tangent y and express them in terms of x's. Basically, they ask us a question in terms of x's. They want to know dy dx, where this is the function y. So give them an answer in terms of x's if you can. And we can, so we will. Okay, let's see, secant y tangent y. You know that in terms of x? Actually, I know part of it. The secant y will just be x itself. So we'll get an x there. The tangent, we need to relate tangent of y to x. That is, we need to relate tangent of y to secant of y. And you know how to do that. Mentioned that a second ago. Let's see. The following is true. You probably read it like this. 1 plus tangent squared equals secant squared. Or if you like, tangent squared equals secant squared minus 1. Tangent squared of y, for our purposes, equals secant squared of y minus 1. So if we take the square root of both sides, we get an however much detail you want to show, we get an absolute value of tangent y equals the square root of this, or tangent of y equals plus or minus the square root. We've taken a square root of two sides, requiring the introduction of a plus or minus square root on one of the sides. So we get tangent y as plus or minus secant squared minus 1. We had this problem in passing when we dealt with the derivative of sine inverse. It's a little trickier to resolve this go around. Okay, so we get tangent y equals plus or minus secant squared minus 1 square root of. Hey, secant of y, that's just x, so we can replace that and get plus or minus x squared minus 1 square root of. So what we've got then is dy dx, the secant of y itself was x, so we get an x down here. And the tangent, I've still got some ambiguity on the tangent of y. We've expressed it as plus or minus x squared minus 1 square root of. So at this stage, we have this idea. We're apparently going to streamline it a little bit more if you look at what we're supposed to get. So we'll have to explain where that absolute value comes from. But at this stage, we know the secant inverse is of this form. Not precisely equal to this. We got to do something about this plus or minus stuff still. Okay, so there's where we left off. Now, what's up with the secant inverse function? Notice from the graph of y equals secant inverse above that the slope of this function is positive wherever it's defined. Let's take a look at the secant inverse. So they're claiming the slope is positive. They're claiming the derivative is positive for secant inverse. Let's go back to the notes, and bring up a picture of secant inverse. Here it is. Yeah, it's always going uphill. Even over here, it's going uphill. So wherever the derivative is defined, that derivative is positive. Tangent lines have positive slope everywhere. At -1, we've got a problem, so the vertical tangent or something, and we've got a similar problem at 1. But remember, those values were being removed from the derivative. Away from -1 and 1, where the arcsecant function is defined, secant inverse, we have a positive derivative, I see from the picture. So I'm relying on the graph to say the derivative of secant inverse is always positive. Be very careful. X itself may be positive or negative. We just observe from the graph that the derivative of secant inverse must be positive. Tangent lines to secant inverse have positive slope. They're going uphill. It's an increasing function. So we need to make sure this thing here is positive. One thing we could do is just slap absolute values on the whole thing. That would do it, and that would give us the absolute value on the x down here. It's written up here a little bit more slowly. If x is greater than 1, then 1 over x times the square root of x squared minus 1, that'll be positive. The square root thing, always positive. The x itself, well, that depends on whether x is positive or negative. If x is greater than 1, remember x has to be greater than or equal to 1 or less than or equal to -1 for the secant inverse even to make sense. Of course, it can't be plus or minus 1 or we'd have division by 0. So that's the restriction, x is greater than 1. When x is greater than 1, x is positive, and we can use this. When x is less than -1, then x is negative. We need to make sure the whole thing is positive. Well, the square root part's positive, 1 is positive, and in this case, x is negative. So we need to stick an extra negative sign out front. Now we've got a negative times a negative times a positive times a positive. The whole thing is positive. So we have to introduce the negative sign there. What you can then say is, well, if x is greater than 1, then the absolute value of x and x are the same thing because x is positive, and we can stick an absolute value there, and that doesn't change anything. If you like, when x is less than -1, then the absolute value of x is negative x. This is positive, right? Because x itself is negative. We've got a negative times a negative under these conditions. So in either case, I can take the sign out front and the x and combine them and replace them with absolute values. So the derivative of secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. Combine it with the chain rule and you get the thing we stated initially in terms of the statement of this theorem. Back to the notes. Okay, so we've differentiated which one's sine inverse, tangent inverse, secant inverse, right? The inverse trig functions, but we haven't differentiated the inverse co-trig functions. We haven't done cosine, cotangent, or cosecant inverse. But, I think we stated this previously, we have the following identities between the 3 inverse trig functions and their inverse co-trig functions. Cosine inverse of x is pi halves minus sine inverse of x. Cotangent inverse of x is pi halves minus tangent inverse of x. And cosecant inverse of x is pi halves minus secant inverse of x. Why was cosine called cosine? Where does the co come from in cosine? Complement. This is explained, I think it's in chapter 1. It should be in your pre-calculus and high school experience as well. Why is cosine called cosine and not something totally different? What's it got to do with sine? And where'd the co come from? Well, the co came from complement. The CO is from complement because complementary angles have equal cofunctions. If two angles add together to give 90 degrees, pi halves radians, then the sine of one will equal the cosine of the other. Complementary angles have equal cofunctions. And for acute angles, it's just because, geez, I look at one angle in a right triangle, what's opposite and adjacent interchange when I look at its complement in the same triangle. So the cofunctions get interchanged. These relationships then tell us if we're going to differentiate these three, we may as well just differentiate this right-hand side. The derivative of these constants, that's all zero. We pick up a negative sign, and then we have the derivative of the inverse cofunctions, cofunction of cosine. So the only difference in the derivative of an inverse trig function and the derivative of the inverse of its cofunction is the negative signs that are going to pop up right there. So if we want to differentiate, here's all six of them. If we want to differentiate cosine inverse, we'll just take the derivative of sine inverse with a negative up front. Same thing with cotangent inverse. Its derivative is the same as a derivative of tangent inverse, but there's a negative out front. Secant inverse, cosecant inverse, same thing. Negative out front of the cosecant inverse. This is consistent with the way you differentiated regular old trig functions before we got into this inverse trig function stuff. The derivative of the cofunctions started with a negative. I'm not saying they're negative. Their derivatives started with a negative sign. Derivative of cosine is negative sign. Same thing here. The inverse cofunctions all have derivatives that start with a negative sign. And the rest of it is the same as the derivative of the corresponding function, corresponding cofunction. So we compare these things off, and it's half the stuff to remember, which is why I said a half hour ago, I'm interested in differentiating sine inverse, tangent inverse, and secant inverse. The other three follow from those three. Okay, let's illustrate that. We'll refer back to this collection of results in the final three. Whereas the punchline is you need to get these in your head because you're going to use them a lot. Derivative of sine inverse, tangent inverse, secant inverse, and then a little trick with the negative signs. So let's illustrate those with some examples. Differentiate, find dy dx when y equals cotangent inverse 1 over x minus tangent inverse x. All right. Shouldn't be a big deal. Here we've got a composition, so we have to use a chain rule on this one. Here we know what the derivative of tangent inverse is. We proved it. So we get as derivatives the following. The derivative of the difference is a difference of the derivatives, so I can break it into small bite-sized pieces if you like. Derivative of cotangent inverse of something would be negative, because it's a cofunction, 1 over 1 plus that something squared. 1 over 1 plus something squared, that's the derivative of tangent inverse. We got a negative out front because it's cotangent inverse. We're using the chain rule because it's a composition of functions. That inner function is 1 over x. We'll rewrite that inner function right there. With the chain rule, quick review, you always differentiate the outer function and rewrite the inner function. Okay, the inner function is 1 over x. I rewrote the inner function. And then, little arrow, I multiply by the derivative of the inner function. What's the derivative of 1 over x? If you like, x to the negative 1. It's negative x to the negative 2. It's this. Get that in your head. We've differentiated 1 over x. You got negative 1 over x squared. Maybe pause the video, convince yourself of that. Right, 1 over x is x to the negative 1. Now you have a power of x. Differentiate that, it will produce this. You don't want to have to quotient rule it. There's a quicker way. We want to streamline this as much as we can at this stage. Derivative of tangent inverse of x is 1 over 1 plus x squared. So there you go. There's a derivative. This can be simplified. This is pretty wild. It simplifies all the way down to 0. Yeah, I bet you. Remember the reciprocal relationship between, say, cosine and secant? There must be something similar to that between tangent. and cotangents, something or other with a reciprocal that's inside there. We're not saying these are equal, we're saying the derivative is 0, which implies a certain relationship between them. We'll explore that in a final example in this section. Anyhow, there's the computations, the derivative is 0. Okay, this is a little bit different. They say find dy dx at the point 0, 1/2 when we have a relationship between x and y is given by the equation sine inverse x plus y plus cosine inverse x minus y equals 5 pi over 6. All right. Instead of just cranking out a bunch of simple little derivatives, they've given us this. Well, what's this all about? They've given us a relationship, an equation relating x and y. So how are you going to differentiate? Well, implicitly, of course. We'll differentiate that equation implicitly, because they didn't explicitly tell us what y is in terms of x. They gave us a relationship, an equation relating x and y. So you got no choice but to differentiate implicitly, which means some chain rule stuff. So that's the point of this question, followed by some evaluation at a particular point. All right, so differentiate implicitly. We'll take the derivative with respect to x of both sides of the equation. Derivative of the sum is the sum of the derivatives, to break it into little pieces. Right-hand side is derivative of a constant, so we get 0 over there. Let's do that one first. Okay, sine inverse. See, we had 1 over the square root of 1 minus the stuff inside squared. So sine inverse of this stuff is 1 over the square root of 1 minus this stuff squared under the square root. 1 over the square root of 1 minus x plus y squared. Ooh, should have a little arrow there. I'm using the chain rule. Chain rule adds to this 1 plus dy dx, the derivative of the stuff inside. Derivative of x is 1. Derivative of y with respect to x is dy dx. Don't forget the dy dx. That's what you're looking for. Same thing over here, except now we have a cosine inverse. Okay, it's the same format, except we'll start out with a negative. So we have negative 1 over 1 minus the stuff inside squared. Stuff inside is x minus y. So we don't get a simple cancellation here. There's different stuff in the cosine inverse than what's in the sine inverse. And chain rule tells us to multiply by the derivative of x minus y with respect to x. And so we get derivative of x is 1, derivative of y with respect to x is dy dx. All right, so that gives us an equation involving dy dx and a bunch of x's and a bunch of y's. All right, so let's see, we've got dy dx times this term. There you go. Dy dx times this term. So there's a negative there and there's another negative here. See, those cancel out to leave us with a positive. This thing times dy dx. We've got this term will move to the right-hand side of the equation, and we've got this term will move to the right-hand side of the equation. 1 over square root of 1 minus x plus y squared, square root of, there it is, except it's negative because it's on the other side of the equation. This thing, there it is on the other side of the equation, except now it's positive because we moved it to the other side of the equation. All right, so we've got this thing times dy dx equals that thing. So to find dy dx, really all we have to do is divide by this, and that'll give us a compound fraction with that thing in it. I'm going to try to simplify it a little bit before we do the division. You want to go ahead and divide? You go right ahead. We're going to plug numbers in, so probably a lot of stuff will collapse. But I'm going to get common denominators and add these two terms together and add these two terms together. Hey, the denominators are the same, so we'll get some simplification from this. All right, so least common denominator would be the product of these two denominators, and that's the case on both sides. So let's do that. We'll multiply this by this thing over itself, and we'll multiply this by that thing over itself. And similarly over here. Least common denominator is the product of the denominators. Getting that common denominator and doing the addition produces this mess here. So product of the denominators in the numerator, we get this stuff. It's the sum of those denominators. And similarly on the right-hand side of the equation. All right, what that accomplished was, you see this big messy denominator here? It's the same as the big messy denominator on the other side of the equal sign. So cross multiply. You can get rid of those denominators. It simplifies down to this. Now we can divide both sides to get dy dx equals the right-hand side divided by the left-hand side, and it produces this. So calculus, that was the easy part. The algebra part's the time-consuming part, but there's dy dx in terms of x's and y's. Could you get it simply in terms of x's? Probably not. Look at this horrible equation they've given you up here. You can't solve this equation for y. You can't. Nobody can. It's unsolvable for y. So you're stuck with implicit differentiation. All right, there's a derivative. They want to know the derivative when x equals 0 and y equals a half. You plug in 0 and a half. Let's see. If we look at x plus y or x minus y, we're going to get 0 plus a half or 0 minus a half. We'll get negative a half, and then it's going to be squared in all four of these. So when you look at 1 minus x plus y or x minus y squared, that's going to be 1 minus 1/2 squared or negative 1/2 squared. It's going to be the square root of 3/4. We'll simplify down to the square root of 3/2. So this thing is a square root of 3/2. This thing is a square root of 3/2. This thing and this thing, all four of these things are square root of 3/2. I'm sorry. That one's negative square root of 3/2. Just to streamline the arithmetic, you don't like that, you plug it in and you go through it real slow, and you'll end up in the same place. We get cancellation in the numerator, we get 0 in the numerator, and the denominator we get, I think, square root of 3 when all the dust settles. But we've got 0 divided by something non-zero, that derivative is 0. So stuff did simplify down once we plug the numbers in. So the point of this one was implicit differentiation as applied to inverse sine and inverse cosine. Oh, and plugging in coordinates of a point. Does this tell you anything about the graph of this function? The derivative is 0. It's got a horizontal tangent line at this point. And that, based on what we've done, that's all it tells us. We could do more stuff and maybe learn some more things, but at this stage, all that tells me is horizontal tangent line because the derivative is 0. All right, one last one, rather vaguely asked. They say, what is special about the functions sine inverse 1 over the square root of x squared plus 1 and tangent inverse of 1 over x? Special. Well, let's say we differentiate them, because this is a section on differentiating inverse trig functions. So I got no inspiration, unfortunately, beyond that. But let's see what happens when we take the derivatives. Maybe they'll have the same derivative or something like that. Okay, so let's differentiate the f function, the sine inverse function. Okay, let's see, this will be a little involved. Sine inverse has as its derivative 1 over the square root of 1 minus the stuff inside that sine inverse function squared. Stuff inside that sine inverse function is 1 over square root of x squared plus 1. Okay, so we get 1 over 1 minus that stuff squared, square root of. Oh, and then the chain rule will tell you to multiply by the derivative of the stuff inside. So we've differentiated the sine inverse part. We rewrote the inner function. Chain rules told us to differentiate the inner function, multiply by the derivative of the inner. All right, let's write that 1 over square root of stuff as the denominator, the x squared plus 1 to the negative 1/2 power. Negative, we put it in the denominator, 1/2 would give the square root. So let's rewrite it like that so it's easier to differentiate. So I don't have to get into some sort of quotient rule stuff. So let's see, we'll rewrite this, and differentiating, we'll bring the exponent out front, subtract 1 from negative 1/2, leaving us with negative 3/2, rewrite the inner function, and multiply by the derivative of x squared plus 1, which is 2x. Chain rule. We use the chain rule twice. When you use the chain rule twice, I would expect to see 3 levels of functions. You see 3 levels of functions here? Outer function, sine inverse. Middle function, 1 over the square root of. Third and innermost function, x squared plus 1. Here's the derivative of the outer function, the negative 1/2, negative 3/2. There's the derivative of the 1 over square root part, and there's the derivative of the innermost function. So yeah, we do have 3 layers of functions. That's why we needed the chain rule twice. You got 5 layers of functions, you'll need the chain rule 4 times. So let's see, you want to clean this up? Yeah, I guess so. They've asked us an awfully vague question. I'll go through this in great detail. It simplifies down to this. We had from that square root, upon getting a common denominator, we get a square root of x squared. What's the square root of x squared? It ain't x necessarily. It's the absolute value of x. So we get stuck with this absolute value of x down here. Can you cancel the absolute value of x and the x? No, not just marking through them. If x is positive, then maybe. Actually, if x is negative, I know how to deal with it. I can't simply cancel those two, but I do know how to deal with the absolute value if I know the sign of x, the SIGN, the positive negativeness of x. Okay, well, there's what we get for the derivative of f, the f function that they gave us. Let's differentiate the g function, the tangent inverse 1 over x. It's a little bit easier. Tangent inverse has as its derivative 1 over 1 plus the stuff inside squared. Stuff inside is 1 over x. Rewrite the stuff inside. Chain rule says multiply by the derivative of the stuff inside. Derivative of 1 over x is negative 1 over x squared. There that thing is again. Treat it as x to the negative 1 if you like. And then we get negative x to the negative 2. That's where that came from. Let's distribute there because that simplifies a little bit. It simplifies to negative 1 over x squared plus 1. Is that the same thing we had before? Let's go back. Did we have negative 1 over x squared plus 1 for the previous one? If x is positive, we did. If x is positive, then I can drop these absolute values, cancel the x's, and we get negative 1 over x squared plus 1. Negative 1 over x squared plus 1. If x is positive, those two derivatives are the same. I guess that's special. Let me borrow a result from the future. It's not the distant future. It's, I don't know, about 3 or 4 sections down the road. We'll see in the future that if 2 functions have the same derivative, then those functions differ by a constant. And that shouldn't be surprising. Certainly, if these 2 functions, the difference of the functions is a constant, then when I differentiate, I get this property here. The converse of that is also true, but we don't have the equipment to prove it yet. We will in section 4.2. So what that means is, if I were to pick any number and evaluate the f function and the g function at that number, whatever difference I get would be the same as the difference for those functions for any x value. They always differ by the same constant. What it means in terms of their graphs, hey, if they got the same derivative, their graphs have the same shape. They may not be the same graph. When I graph y equals x squared, that's a parabola. I graph y equals x squared plus 7, that's a parabola that's the same shape as the y equals x squared parabola. It's just displaced, it's translated. Similarly, we'd get these 2 functions have the same shape if they have the same derivative. Turns out if you plug 1 into the f function, you get out pi fourths. If you plug 1 into the g function, you also get out pi fourths. Actually, they are the same functions. This offer only valid when x is positive. So what we just found out is f of x equals g of x, provided x is greater than 0. When x is greater than 0, they are the same function. What happens when x is negative? By the way, x can't be 0. We had some 1 over x stuff in the conversation, so x equals 0 is not an option. What happens when x is negative? Let me go back to the previous slide, and we had the derivative of the f function was negative x over the absolute value of x times x squared plus 1. What if x is negative? If x is negative, I can't just drop that absolute value. I'd have to replace the absolute value of x with negative x if x were negative. Negative times a negative is a positive. The absolute value of x is the same as negative x when x itself is negative. And then we could cancel the x's and the negatives and be left with 1 over x squared plus 1. So this equals 1, positive 1 over x squared plus 1 when x is negative. So it's not the same as this. It differs by a negative in that case. So on to the next part. For x less than 0, the derivatives differ by a negative sign. Or if you like, I could add the function's derivatives together and get 0. Guess what? When the derivative is 0 like that, again, we've got that those functions differ by a constant. I won't bore you with the details. I've also plugged in an appropriate negative value, -1 this time. It produces nice numbers in both cases. And we get out that actually these functions are not equal, but one is -1 times the other one when x is negative. Pretty subtle. The solutions manual, I hope they got all this stuff right. These details are correct. It was more straightforward when x is positive. I could just drop the absolute values. When x is negative, I can't just drop the absolute values, but I can get rid of them. I can't just drop them. I get rid of them by inserting another negative sign, it turns out. And we get that f of x is the negative of g of x when x is less than 0. So that's what's special about those functions. A vague question, but a very thorough answer. It had to be a question we answer in terms of taking derivatives. So there's a way to relate those functions, a special way to relate them, especially if you'll let me run ahead and borrow corollary 4.2 from chapter 4. I can draw this conclusion here. Otherwise, I'm just stuck with the fact that they have the same derivatives or the negatives of the derivatives. But I can go a little bit further with some additional information. And that completes, excellent, that completes section 3.9. So let's end this section the way we started it. You're good at differentiation. You know as much about differentiation as I do. Maybe that ain't saying much, but you're up to date on differentiation. You got it. There's nothing new to be learned about derivatives. There's some other people out there dealing with some more involved functions and some special functions, and you don't know how to differentiate those. And I don't recall any of it myself either. But this will get you through your graduate curriculum in terms of taking derivatives. You know everything there is to know about derivatives. So next, let's use derivatives. So we'll start with applications of derivatives in section 3.10. All of chapter 4 is devoted to applications of derivatives. So now we're going to use derivatives for the next probably 7 or 8 sections. And then in the final chapter of part of Calculus 1, chapter 5, we'll look at something called antiderivatives and integrals, which is in a sense differentiation backwards. Turns out that's way complicated. You got a lot of stuff to learn about antiderivatives. It's so involved, it'll take a good chunk of Calculus 2 for you to come up to speed on anti-differentiation, on integration. But you're good to go on differentiation. And on to section 3.10, and we'll use this stuff for some real-world applications. Have a nice day. I'll see you in section 3.10, related rates.